I hope it's recording. So Turing introduced these with this argument that this sort of any computation can be modeled this way. So actually he said, because if you think you have some little person sitting at a table doing computations, this person has paper and a pencil and an eraser. Maybe it's squared paper. And the person has a finite brain. I mean, has a finite memory, has a finite number of states the person can be in. Turing didn't actually say this is the case. He argued that, yeah, this seems to be the case. So the argument that this actually captures the notion of computation is called the Church-Turing hypothesis. And the important thing is, that's not a statement of mathematics. That's a statement of physics. They're saying there is no way to compute, that there's nothing you can compute that cannot be computed this way, very slowly, but this way. So there's a stronger version, which is the Church. It's called the strong Church-Turing hypothesis, which says that anything that can be computed in polynomial time can be computed in polynomial time on a deterministic Turing machine. Okay, because if you have multiple tapes instead of one tape, how much does that help? Not more than a polynomial factor. If it's infinite in one direction instead of two directions, how much does that change things? Not more than a polynomial factor. What if it's not even easy to figure out how you would implement an infinite two-dimensional tape. How much would that speed it up? Not more than a polynomial factor. How much would it speed up to be able, I mean, basically everything we do, everything we've ever come up with only speeds it up by a polynomial factor. The strong Church-Turing hypothesis said anything that can be computed in polynomial time can be computed in polynomial time on a deterministic. Sorry, that's not, what I just said is not true. Non-determinism. I have to say this very carefully. We've never come up with a model of computation that's more than a polynomial factor faster than a deterministic Turing machine. No, even that's not true. I'm probably going to have to re-record this section, but some non-deterministic Turing machines, right, where you guess, and then, I mean, where the finite state control is non-deterministic. I hope you saw non-deterministic finite state machines. Then it says yes if there is some path through the computation which leads to an accepting state. Okay, so it's like a non-deterministic finite state machine, but it's more powerful. It has this tape, which makes it amazing. We don't know how to build that. Right? We've never come up with a model of computation we can actually build that's more than a polynomial factor faster than a deterministic Turing machine. Maybe. We don't actually know if quantum computers are more than a polynomial factor faster. We do know that there are things we can do in polynomial time on a quantum computer that we do not know how to do in polynomial time on a deterministic Turing machine. And that's one of the reasons everyone's so excited about quantum computers. Two things are, we're still not sure that they actually work. I hope Sarah isn't watching this. But also various physicists will get extremely angry if I say it. But I'm not convinced they actually work. I mean, it's been announced, there's been like a Nature paper about all this stuff, but it's like, yeah, I'll believe it when I see it. And the other thing is, the stuff that they can do in polynomial time, that we don't know how to do in polynomial time on a deterministic Turing machine, we don't have strong evidence that you can't do it in polynomial time on a deterministic Turing machine. For example, we don't know how to solve, at least as far as I know, we don't know how to solve NP-complete problems in polynomial time, even using a quantum computer. For example, SAT. And if somebody figures out a polynomial time algorithm for SAT, a polynomial time quantum algorithm for SAT, that will be a really big deal. And that will either sort of convince me that they don't work, or it will really alarm me. But maybe they won't work in parts. Okay, so, okay, that was only 6 minutes. So wait, so Turing came up with this model. So he said, imagine somebody sitting at a desk, has paper, a pencil, an eraser, a finite memory, a finite number of mental states. Big, maybe, but finite. But an infinite stack of paper. So what can this person do? Can check the contents of, like, graph paper, can check the contents of a cell, and that changes the mental state. And they can sort of, now maybe it can be two-dimensional, but you can simulate this with, because you say, okay, each cell is actually a piece of paper, so the character is actually the assembly of all the characters you could write on that piece of paper in the squares. Okay? And so he got this argument that this is a good model of computing. And people would say, okay, what if you have this? What if you augment it with this? What if they have different colored pencils? What if they have this? And everything people could come up with, it doesn't change it. I mean, it doesn't change it. It doesn't, we've never come up with anything that really changes, that can be computed, that can't be computed by a Turing machine slowly. And we've never come up with anything we can build, that we know we can build, that we know speeds is more than a polynomial factor faster than a deterministic Turing machine. This is not what I usually do for a living, but it is pretty cool. And so now I have 17 minutes, and I forget what the third thing, because I've said sort of Cook's, so the assembly language version of Cook's theorem is that accepts this language of given a program, that is there an input that makes it say return true in polynomial time, accepts. I mean, obviously you can reduce lots and lots of problems to accepts, because given a clique, given a graph, and you say does it have a clique of size k, you could write a program to check a solution. Given a graph and ask does it have a vertex cover of size at most k, you could write a program that would check a solution. So for any problem where you can check a solution in polynomial time, you can reduce it to accepts by writing the program. And then you can reduce accepts for machine language to SAT. You can reduce SAT to 3-SAT, and you can reduce 3-SAT to all those other problems. So all of those problems are NP-complete. NP-complete, right, that was the other thing I wanted to say. And then we went through this Turing machine stuff. You can find out loads of stuff about Turing machines. As I said, I don't really need you to know about Turing machines, except maybe a little bit for the stuff we're going to talk about on Wednesday. But I do need you to sort of know something about Turing machines. I mean, when I was an undergrad, my professor made me, it's like writing assembly language programs. Certain sadistic professors think that you have to do this to be a real computer scientist. So they would, like me actually, in the fall semester, I made people on the assignment, I made them design a Turing machine. I'm not going to make you design it. I'm still writing assignment 4. I could put a Turing machine on there, but I'm not going to. But I need you, if people say like, ooh, the pinnacle of theoretical computer science is the Turing machine, just nod, okay? Like, don't argue with them. So there are lots of different ways of doing this. Like sometimes you have to move and sometimes you don't have to move. So sometimes you're allowed to stand still and some models you're not. It doesn't really matter, they're all equivalent. So, and there are enough that you can pretend not to know exactly which the person is talking about. But yeah, pretend that you know Turing machines. Don't tell them that you learned Cook's theorem in terms of assembly language or C or something like that, because otherwise they're going to think you're some sort of weird radical. So, right, in the remaining, how many minutes? 14 minutes. I want to talk about sort of our view of the universe. Okay, so you have what's called P. And these are the problems that we can solve in polynomial time we know how to solve in polynomial time, that you can solve in polynomial time on a deterministic Turing machine. So that means basically your computer, right? So if you can write an algorithm that works given a yes/no problem, you can write an algorithm that answers this, that says yes or no correctly in polynomial time and the size of the problem instance, then it's in P. Okay? There's a bigger class, which is NP. Maybe I'll write this inside. No, I'll write this outside. NP is the class of problems for which you can solve them in polynomial time on a non-deterministic Turing machine. That means you can check a solution. Some people say it's not polynomial. That is wrong. Okay, that is wrong, because it includes P. It includes the stuff that we can do in polynomial time. It means non-deterministic polynomial time. Never ever, I hate failing students, but people who say NP is not polynomial, I'll make exceptions. So then you have, so this, I'm trying to remember exactly how this goes. It's in the scribe notes for reductions, correctly, I believe. So this is what's called NP hard. So this means these are things such that if you could solve these, then you could solve everything in NP. Okay. Now note that it doesn't contain all of it. It doesn't contain P. That we think this is the way the universe looks. Okay. Because if you could solve any of these, then you could solve everything in NP. So if it included P, if you included anything in P, then everything would collapse into, well, all of NP would collapse into P. So this is NP complete, which means it's in NP. So given a solution, you can check it, and you can check the solution in polynomial time. This means the way we've been doing it, you could reduce it to SAT. It's one of these things where it has you can write a propositional formula that says this is a yes instance. But now that we've seen accepts, we can just say you can check a solution, and you can write a program that would check a solution in polynomial time. And so it's in NP, and also you can reduce everything in NP to it, which means you choose your favorite NP complete problem, and you do this reduction. You do this where you say, okay, given an instance of my favorite problem, clique, I show how, and now I want to show that. Okay, I don't know this new problem. Okay, well, you see, like that student at Alta did, where he said, okay, ham path on grid graphs is known to be NP-complete, and so he reduced it to words 2. So all of these where we knew SAT, so Cook's theorem is that SAT is NP-complete. You could reduce accepts to SAT. So then you can reduce, so you choose say 3 SAT, and you show that, so we know 3 SAT is NP-complete, and we reduce 3 SAT to clique. That means that clique, once we've shown that clique is in NP, then clique is NP-complete. So these are 2 things that you have to show. One, it is in NP. This means if you have this problem X, it reduces to SAT. I mean, actually, it reduces to accepts, but this is sort of how we think of it, how you can think of it. And 2, you can reduce an NP-complete problem to it. Which means you can go from SAT to X. Now maybe you're not going to reduce from SAT, you're going to reduce from something else, you're going to reduce from clique or 3-colorability, whatever. But remember, you can go from clique, from 3 SAT to 3 SAT to clique, and then to X, which means you can go from SAT to X. So this, remember, if you have this direction and this direction, then it's sort of part of that network. You can get from it to SAT, you can get from SAT to it. So, for example, 2-colorability, you can reduce it to SAT, but we don't think you can reduce SAT to it. Because if you could, we can solve 2-colorability in polynomial time, so all of the NP would collapse into P. Non-deterministic Turing machines would be only as non-deterministic polynomial time Turing machines would be only as powerful as deterministic polynomial time Turing machines. And for any problem where you could check a solution in polynomial time, you could solve it, you could find a solution in polynomial time, and basically crypto would cease to exist. I always recommend that people go out and watch this movie Sneakers with Robert Redford, James Earl Jones, River Phoenix. If you don't know who River Phoenix, James Earl Jones. In some of my classes, they didn't know who he was until I said the voice of Darth Vader. River Phoenix was the brother of Joaquin Phoenix, who's the Joker. Robert Redford, if anybody ever seen Butch Cassidy and the Sundance Kid. Ben Kingsley, Dan Aykroyd. It's a great movie about cryptography, about factoring. Anyway, all of that stuff would happen, and more. So this whole, in 6 minutes, so the question of whether or not the universe looks like this is called P equal NP. Because we don't know that this is a proper subset of NP. If somebody finds a polynomial time algorithm for any of those problems, then there's a polynomial time algorithm for all of those problems, and this will collapse. There will still be stuff that's NP hard. But NP complete, everything in NP will be NP complete with 2 small exceptions. Which is the language that contains nothing and the language that contains everything, and those are exceptions for just stupid technical reasons. Which I went through in the fall semester, but which I'm not going to go through now. Because I have 5 minutes. So this is the P versus NP problem. This is worth, it's one of the Clay Math Institute. So around the turn of the millennium, 20 years ago, The Clay Math Institute posted 7, 8 problems that they said. So they were redoing something a mathematician called David Hilbert did at the beginning of the 20th century, who said, he gave a list of problems. He said, these will be the problems mathematicians work on for the next 100 years. And he was more or less right, though it was wrong how a lot of them would turn out. So the Clay Math Institute picked like 7 or 8, I think 7, problems, and said these are the big problems in mathematics now for this century. And one of them was P versus NP. So this was Noah Cook, who is at Toronto, and so his name has come up before because you remember when we were talking about Karasuba, and I said if you cut it into 3, that's called Toon Cook. Well, Cook is the same Cook, okay, Steve Cook, who was a PhD supervisor of some friends of mine, and won the Turing Award for this stuff, and is very cool. So just in the remaining, like however many minutes, 3 minutes, well, okay, I mean it's 25 minutes, it's 75 minutes, so actually I get 5 bonus minutes, because I'm allowed to actually talk for 80 minutes in a lecture. So this is one possibility. Of course, the other possibility is that it looks like this. NP hard, and then you have P equals NP inside. There's stuff that's NP hard that's outside NP, which I don't have time to get into in this course. So there's something called P-space, which is what you can compute in polynomial space instead of polynomial time. And I think we know that P-space, there are problems in P-space that you cannot compute in polynomial time. They're solvable. I mean, they're solvable using polynomial space. But P-space complete problems are known not to be in NP. So regardless, so they're known not to be, we know they don't have polynomial time solutions. You might think that these are super weird problems, but for example, chess, certain versions of generalized chess on like n by n boards are P-space complete. Lemmings, and recently I can send you an article showing that Angry Birds is P-space complete. So basically, for P-space complete, you sort of have moving parts, and you're allowed to set them up in clever ways. We also know that there are, beyond P-space, there are problems you can't do. There are problems, which is what we're going to talk about on Wednesday. Problems, incomputable things. Incomputable, assuming that the Church-Turing hypothesis is correct, which means that you can't compute things that can't be computed on a Turing machine. It's weird doing this without anybody, but I'm sorry about that. So that is sort of complexity theory. I hope you now have some sort of idea why this is cool. On Wednesday, pseudo Wednesday, we're going to do computability theory. In particular, we're going to do Cantor's diagonalization. Just to get you familiar with this idea, this thing's called diagonalization. Then we're going to do the halting problem, the Entscheidungs problem, which is what Turing sort of invented Turing machines for. And then we're going to talk about Kolmogorov complexity. You've actually heard that name before when we were talking about Karasuba. Remember Karasuba, he heard this conjecture that we couldn't do multiplication in better than quadratic time from some professor giving a seminar, and then he went off and solved and did it in subquadratic time. and came back, and the professor was very impressed and went off and wrote the paper without Karatsuba knowing and sent it in. That was Kolmogorov. Okay, so he is, he's a huge figure in mathematics and statistics. Cook is a huge figure as well in this. I was going to say also Turing. I mean, you can't get away from Turing. Turing is, the Turing Award is the highest prize in computer science, if you do AI, you probably end up hearing about the Turing test, which is about how to distinguish an artificial intelligence from a human. And that, if you think about it, which now that I'm completely out of time, I don't have time to talk about, but Turing was thinking about computation and sort of, okay, I mean, if you think about that person sitting at a desk, and so what does it mean? I mean, can you compute things that you can't do in this model and that you can't sort of mechanize? And then the Turing test actually has sort of a similar flavor. So that's not just that he was sort of busy in two fields. To him, there wasn't that big a distinction, which is kind of cool, because now, I mean, when you're at the low levels of theory and AI, they sort of clash, and then, but actually, all the really hotshot AI people I've known were also incredibly good mathematicians, and they knew this stuff backwards and forwards. I mean, Jeff Hinton is actually related to George Boole. So I think I read that somewhere. I don't know. I should have asked him. He was at Toronto the same time I was a student there, but I never did. So thank you for listening. I hope somebody listens. Now I should go off and write assignment 4. So I guess this is how lectures are going to be from now on. And unless, I don't know. Right. If you have questions, please ask me. So I will probably be hanging around. I'm not sure. Yeah, I will be online at the times. I will have office hours, I guess, at the times. Maybe I will shift it a little bit, because that way I can the stuff happens on a Wednesday at 11 o'clock, so maybe I can be half an hour late. But yeah, please email me, and there's not so much complexity theory in the book, but there is complexity theory in the book. Okay, the thing is just going to stop recording while I'm talking, so don't worry about it if this just ends. Okay, so see you Wednesday.